So when you get to this point and you've solved for your moles to figure out how much you need to make a solution, you're going to take your moles and multiply by what? Molar mass. We did a problem yesterday in class where we had sodium sulfate. What's our formula for that again?
Na2SO4.
All right. Na2SO4. The molar mass of that we said was what?
119.08.
Nope. 142.05 grams per mole. So instead of dividing by our molar mass in the beginning to figure out our moles to get our molar solution, in this problem we are waiting until the end to multiply by the molar mass. And when we multiply our number of moles by our molar mass, what is our final number of grams? 17. So we can round it to one decimal place, all right, to kind of stick along with sig figs. 17.8 grams of Na2SO4. But, as we just said, that's not our final answer because it's asking us to explain how we would make it. So we would take 17.8 grams of sodium sulfate and place in a container and fill to 250 mils. And then we'd have our 0.5 molar solution of sodium sulfate that we could then use for whatever experiment we're doing. Now we're going to talk about our other calculation, folks. All right, and again, like I was saying yesterday, that molarity equation that we talked about yesterday, I've done that probably thousands of times. This one, I've probably done just as much. So you'll make a solution, but you may already have a solution made up that you can then dilute down. So this is what we're talking about, molarity by dilution. A lot of times we're doing acid-base chemistry, which is going to be our next unit that we will get into right before break, and then when we come back from break, we'll talk about it. But why? First off, what does dilute or diluting mean? To make it down? Less to weaken it, right? To make it less, the strength be weaker. Absolutely. So, who can think of an example of something you might want to dilute in your everyday life? Salt? Orange juice? Any type of juice? Gatorade? We talked about that yesterday, right, with G2? Cranberry juice? Any type of juice? All right? Absolutely. Sometimes, if you're cleaning products, you may have concentrated ammonia or concentrated bleach, and you will need to dilute that down to make like a bleach solution that's okay to use on countertops and things. All right, that's pretty much what you're doing when you buy like a bleach spray in the store. They take concentrated bleach, they dilute it down to whatever concentration they need that's safer, so that it doesn't, bleach everything that's in sight when you are using it to clean. But anyway, you get that idea. All right, it's used a lot of times in life. All right, so here's our formula. What formula does it look like? It looks just like Boyle's law. So, if it looks like Boyle's law, what type of relationship does molarity and volume have?
Inverse.
It's an inverse relationship. All right, so you can, again, just like with Boyle's law in our last unit, you can kind of check to see if you've done the calculation correctly. Because if molarity goes down, what should happen to the volume? It's what? It goes up, all right? It's the opposite effect here. So as far as a mathematical standpoint goes with these problems, folks, should not be super difficult. The hard part is going to be the terminology, especially early on, until we get more comfortable with it. So let's jump into an example. How much 12 molar hydrochloric acid is required to prepare 300 mils of a 5.0 molar solution? Here's the deal, guys. It doesn't matter which one you call M1 and V1 or M2 and V2, as long as you get the correct two together that talking about the same solution. Does that make sense? All right? You've got to get the pieces that go together. It doesn't matter if you call them 1 or 2. The math is going to still work out to be the same. So when it says how much 12 molar, when it says how much, what are we looking for here? Volume, right? So looking for a volume, but it's saying how much of this concentration. So this molar concentration is going to have a volume to go with it. It doesn't matter if we call this V1 or V2 or M1 or M2, as long as it's the same subscript. Since it's the first ones that I see, I'm going to say V1 equals a question mark, M1 equals 12 molar. All right? And it says is required to prepare 300 mils of a 5 molar solution. And then we can see that, hey, those go together as well because it says of A. That's kind of the key that's linking those two together. So V2 is going to be 300 mils. And M2 is going to be 5.0 molar. Now, what have we done already, folks, with volume in this unit? Change it to liters. Do you think we have to change it to liters in this problem?
You don't have to.
Now, you don't have to. There it is. But I encourage you guys to be consistent. Anytime in this unit that you see a volume, change it to liters right away. It's easy to go between mils and liters, right? Divide milliliters by what to get 2 liters? 10 to the third, all right, 1,000. So guys, if you leave it with milliliters in dilution, it's okay. But you can't have milliliters when you're doing a molarity calculation. That is the big deal there. You have to have liters when you're doing M over V. M equals N over V. So here, I'm just going to be in that good habit. 0.3 liters. All right, here we go. M1 V1 equals M2 V2. I'm looking for V1, so I'm going to divide by M1. So V1 is going to equal 5.0 molar times my second volume, which is 0.3 liters, all over my first molarity of 12 molar. When I do that math, what do I get? 0.125 what? Liters. Is this anything brand new for us, folks? No, it's not at all. You guys do the U-try problem. All right, so this one, folks, may be a little more challenging to identify, but here's the key that links them together. It says 35 mils of 15 molar. So you know that those two go together. It doesn't matter, again, if you call them V1 and M1 or V2 and M2, the math is still going to work out the same. So I'm going to call them M2 and V2, just to prove a point. So this is going to be 15 molar. This is 35 mils. And by you writing out, okay, I'm identifying my variables. I know which ones they are. That's why the math is going to work out just fine. All right, that means 6 molar here, and that means I'm looking for the other one, the other volume. All right here. So V1. So M1 V1 equals M2 V2. Divide by M1. V1 is going to equal, we take 15 molar, we're going to multiply it by 35 mils, all over M1, which is 6 molar, M's are gone. When I do this math, 15 times, you left it now, you converted it to liters, guys, what should your liters be? Not 0.35, 0.035 liters is what you should have, all right? Now, I left mine as milliliters, guys. That's okay, because it's going to be the same thing as liters, except they'll just be off by a factor of 1,000. When you do it, if you did it with liters, what do you get for your answer? 0.0875? All right, liters, well, that would just be 87.5 milliliters if I did it my way. Again, I encourage you guys to be consistent. Keep it as liters every time, but if you leave it as milliliters here, you're okay. You just have to remember for sure that when you do the molarity calculation we learned yesterday, it has to be in liters all the time, because it's moles per liter of solution. It's our definition of molarity. Questions? Easy? All right, we're going to talk briefly, guys, about a couple other types of concentration units. Molarity is one that we're going to talk about extensively, but you've got a little bit of information there on the next page in your notes about this thing called molality. So it sounds just like molarity, except molarity was a what type of property? Extensive, right? Means what? What does extensive mean again? It changes based on what? Amount, okay? So, molality, guys, is an intensive property. And what makes this an intensive property is that it's all mass-based. The other one was moles per liter, guys. Volume is something that can change based on temperature. And we talked about that in KMT. What happens when particles start moving faster? They tend to what? Collide more. That's one piece. That's pressure. But what happens to their volume? It increases, right? As temperature increases, guys, so does volume. That's Charles' law. They start to spread out more. So, molarity can actually change based on the temperature. Molality will not, because it's all based on mass. And mass, no matter what temperature you have, will change. Now, we're not going to really do too many calculations with molality. I'm introducing it here, guys, because molality is only used in certain special occasions. Typically, if you're on like an industry line, and you're making a ton of, huge, large-scale production for, let's say something like toothpaste or whatever, right? Really? That's really weird. Now I'm thinking. Now, do you know what I'm thinking of now? Since we're talking about toothpaste. What kind of toothbrush?
Oral. I don't know. That was so weird.
That's really weird. Tooth tunes is what I was thinking. Because we had that conversation in this class. It was this class, right? We talked about tooth tunes?
No. Tooth?
Yes, it was, because it was him, wasn't it?
No.
Oh, is that like the kid?
Anyway, folks, what molality does is when they're on a big industry line where they're producing, metric tons of things, a lot of times the temperature is a lot higher there. So they will do their calculations based on molality because, again, it's intensive and it's not going to change based on temperature. Volume will change based on temperature. It's the whole point of me talking about this. I know in your notes it talks about molality. We're not going to worry about it, though. Okay, we're not going to do the calculations. It's there for extra information. We're not going to worry about it. The other thing I want to talk about very briefly, guys, is other concentration units that are used. We're not going to use any calculations with them. Okay, we're just introducing it. Those of you who take AP next year, you may see molality. You definitely will see mass percent. All right. But again, very similar concentration units that we've used in other locations. Mass percent is just a weight percent. Mass of your solute, total of the mass of the solution. Part over whole times 100. Mole fraction is one that is used a lot of times as well. It's a little more complex, all right? Moles of the part of solution we're talking about divided by the total moles of your solution. It's percent based. So when we talked yesterday about IV bags, right? I asked you guys who's had an IV in their arm before. A lot of times you're dealing with liquids because molarity can change based on temperature. Those are based on percent, like weight percentages, those concentrations in the bag. If you looked at it, I've never had an IV in my arm, but for those of you who have, can I see hands again really quick? Okay. Did you ever look at the bag while you're sitting there? Did it ever say like a 1% by volume or something like that? Concentration? No? Maybe you didn't look that hard? Yeah, you probably are thinking about a lot of other stuff, right? I was just curious. But guys, listen, those bags a lot of times are based, their concentration is based on weight percentage, right? Shh, really quick. So, all that to say, there's a lot of different ones. The one we're concerned about in this class, though, is molarity, because we're going to use it in our next unit when we get to acids and bases, and you guys do what I think is the best lab of the entire year. I know I said that with the last one, that was sarcasm when we boiled water, because that was like watching paint dry. But the next one we will do when we get back from break is called a titration. You guys will actually finally feel like scientists. We're actually doing a lot of stuff like you would see them doing in a lab.
Like explosions?
Not explosions. We talked yesterday that explosions don't happen. Anyway, folks, you're working on your homework now.